Hello everyone. Today we'll be solving 3613. I did look at the solution a couple of days earlier and I thought it was really interesting. So I just wanted to share it with all of you. So you're given an undirected connected graph with n nodes labeled from n minus 0 to n minus 1. And you're given an integer array edges which contain the nodes which the node which are connected u and v and the weight of the node, weight of the edge. Hmm. And along with that, you're also given the integer k. You're allowed to remove any number of edges from the graph such that the resulting graph has at most k connected components. At most k. Okay. The cost of the component is defined as the maximum edge weight in that component. And then return the maximum possible cost of the components. So what we're required to do is we can remove any number of edges from the given graph. And initially it's a connected graph, so the number of components is one. So what we're required to do is uh, disconnect components, disconnect edges such that you form k components. And after you form k components, return the weight of the, uh, like the maximum weight of any edge. So here we disconnect 4 by removing the edge which connects 3 and 4. And then we return the maximum weight. So here we remove this and we get the maximum weight is 4. So there are multiple ways to solve this problem. And what we'll be doing today is uh, related to union find. So union find is a graph algorithm which helps you, which deals with counting the number of components. So anytime when you have to count the number of components, most of the times you can use this algorithm. So how we're going to solve this is, uh, let's look at the problem in a different way. Let's assume um, we all the components are not connected. So that would be a disjoint set union. That's what it's called. So it's called a DSU, disjoint set union. So for this example, let's say 1, 2, 3, 0, and 4. So 1, 2, 3, 0, and then we have 4. So let's say the edges are given. So we can rephrase the problem as use these edges and keep connecting the nodes such that you end up with k components in the end. And you may or may not use all the edges. So here, let's say we start with 0 and 1. We connect this. And initially we had 1, 2, 3, 4, 5 nodes. And now we have 4 components because we connected 2 of them. And then we connect 1 and 2. And we have 3 now. And k is 2. So we can connect one more. So let's connect um, 1 and 1 and 2 now. 1 and 3. So now we have 2 nodes. And then we return the uh, edge with the maximum weight. So the input graph, what we're supposed to do is we can sort, let's say this was 14. So it would be meaningless to connect 0 and 1 because it has the largest weight. So you'd rather disconnect 0 and 1 and then connect this, which has a weight of 6, and then you'd return the value 6. So what we're required to do is, until we get k connected components, we keep connecting the edge with the smallest weight. So in this example, we have 2, so we connect 1 and 3 first with the smallest weight. And then we connect 1 and 2, uh, and then 1 and 4. So until we reach component number 2. So initially we have 5 components. You connect 1 and 3, you have 4. And then you connect 1 and 2, you have 3 components. And then after you connect 1 and 0, you have 2 components. So that's how you'd solve this. So if you haven't done union find before, this might be a little confusing, but then I don't think it's too hard. You can follow along. So first, what I'm going to do is I'm going to declare a class called disjoint set union, and this is basically when we declare an object of this class, we're going to create n nodes which are not connected to each other. So let's say uh, let's define it. So define init, then we'll take the input, which is an integer. Okay, so let us uh, so usually in union find we have two functions. One is called find, and the other function is union. So each component, so let's say 1, 2, 3 are connected to each other, and then we have 4 and 5. So each component is represented with the parent node, and we can assume the parent node to be anything here, but in general, we assume the smallest node value to be the parent node. So let's say 1 is the parent node here. And then if the parent of 2 is also 1, then that means it belongs to the same component. So we can iterate through all the nodes and find the number of unique parents, and that would give us the number of components. So initially, when we define this object, we need a parent, the parent node that particular uh, of that particular node. So let's say we need the parent node of 2, that would mean it's 1. So we need a dictionary which contains the parent nodes of every node. So initially, since this is an undirected graph, every node is connected to itself. Yeah. So initially, let's just say parent is no node node for I in range of n. Okay. So now we're connecting 1 to 1, 2 to 2, 3 to 3. That's what we're doing now. Yeah. And now let's move on to the next function. We can add stuff if we need to later on. We'll call this find. So find of some node called x. Okay, and then x is also an integer here because our nodes are integers. Okay. So and this we can do it recursively. So let's say we have another node which is 7 here. And if the parent of 7 is 2 and the parent of 2 is not 2, that means it's not the root node. So that means our base case would be if if pair okay if self dot okay, first of all we might have to call the function. Yeah, yeah. So self dot parent, we need self. Basically, we need the object to access this function. So that's why we need to add self there. So self dot parent of n is equal to x. So that means it's the root node. So we return x. And if not, parent of x is equal to find of x. And this is called path shortening. You don't have to get into this now, but then, uh, or you can just, for now, you can just return find of x. But this would optimize it a little more. So I'm just going to add it for now, but don't worry about this right now if it's a little hard to understand. And this is our find function. So now let's define our union function. And this takes two integers. So we'll call it x and y. I hope it's recording, yeah. And what our union function does is, let's say we want to connect the nodes 2 and 4. And if we want to connect them, what we can do is we can use the union function. So if their parents are different, so let's say the parent of 4 is 4 itself and the parent of 2 is 1. So when we're connecting these two nodes, we have to change the parent of 4 to 1 because 1 is smaller. And when we connect this, we need the smallest value to be the parent. So let's first get the parents of both the nodes. So root of x is equal to, let's say, find of x, and make sure this is not parent of x. So let's say um, there was another node, intermediate node, which was 0, not 0. Let's just say it was like 5, 1.5, because there's no number between 1 and 2. And here what would happen is that the parent would return 1.5, but the actual root might have been 1. So you never know. So it's you just use find of x. Root of y is equal to find of y. And now okay, my audio stopped working, so I had to pause it. So if they're already connected, that means we can return false because we aren't really adding another node. And that would be helpful for counting the number of components later. So if root of x is not equal to root of, or let's just say it's equal to, is equal to root of y, then we return false. You don't have to do anything. And if they are not equal, so let's say if root of x was greater than root of y, then we change root of x to root of y because we're connecting them together. And if that's not the case, we can just root of y is equal to root of x. Right. So if root x is greater, then we change root x to the smaller one. And then in the end, we can return true because they weren't connected before. So this is our union function. And now let's move on to so first we need to sort the edges because we might not have the least weight in the beginning. So let's say sort edges dot sort, then key is equal to lambda x such that we need the second index, right? So 0, 1, 2. Sorting uh, using the weight. So let me just get this to the middle. Okay, so and now what do we do? So we need to define an object of so let's call it disjoint set union is equal to dsu of n because it has n nodes. And then hmm, so the parent is already defined now. So initially we have n components and we need to, so let's call it number of components. Let's call it components. Initially it's n and we need to bring it down to k. So let's say uh, while components is greater than k. So when it's equal, we stop. So when it's greater than k, uh, we we have to join the nodes such that the edge weight is the least. So we iterate through this. So let's say I is equal to 0 initially. Okay, and then we join. So dsu dot union. Let's call it x comma y is equal to x comma y, and then we need the weight comma weight is equal to edges of I. Okay, and we unify DSU dot union of X and Y. And if they weren't connected, so let's say let's assume 4 and 2 were different components. If they weren't connected, that means initially we had two components, and after you connect them, it becomes one. So if it's true, that means we're reducing the number of components. So if if that returns true, we decrease the number of components here, right? And yeah, that's it. So in the end, we have to return the last edge you connected because that's the greatest edge. So return W. Yeah. So that seems right. So let's try for node for I. Okay. For node in range n. Okay. So self dot parent is equal to this. It's not a function. It's a dictionary. That's a silly mistake. So please don't learn that from me. Okay. DSU. It takes three. Okay. I forgot to pass self because we're calling it through the object of this class. So we need to pass in self. Find is not defined. Okay, self dot find. Self dot find. Yep. Here too, same mistake. That seems fine now. Okay. So there is a small mistake. Let's correct that. Output is 2. Expected is 4. Okay, so let's just print out the edges we're connecting. So x comma y comma w, and then let's also print out components. Okay, so initially we had so number of components is 432, which is right. And why is W2 all the time? Okay, we have to. Okay, we're iterating through this. Okay, first of all, if I connect the same thing again, why is the number of components decreasing? Return false. If root x is equal to root 5, return false. Okay, if is equal to true, let's just print. That shouldn't happen, right? So 1, 3, 2. 1, 3, 2. Okay, let us just also print parent uh, tsu dot parent of x and tsu dot parent of y. And let's see what's going on. Okay, so the parent is 1 and 3, 1 and 3. Okay, so if root of x, okay, I got another mistake. So the mistake we're doing is we have to change the parent of this particular node. right? So we have to change the parent, not the root. Not the, yeah, we're just changing the local variable here, which is just stupid. So we have to change the parent of x is y, root y, and then parent of y. So that was a logical error, and now we obviously have to increment I as well to make it work. So now self-parent, stupid mistake. Mm, that was clumsy. But yeah, I hope it's recording. Yeah. Okay. Yeah. Maximum recursion depth increased. Yeah, that's because we're we're not incrementing I, and that is wait, no, never mind. Parent of x is equal to self dot find of x. Let's just print parent of x here. And yeah, I think this part is fine now, so we can remove this and just increment our pointer, which is pointing to the edges. So whenever we take this, I plus equal to 1. Yeah, so there's something wrong here. Okay, 0, 0, 0. First of all, and we also need n, right? Oh, sorry, x. Okay, so the parent is parent of x is 0. Okay, so okay, never mind. The problem is it's stuck there for some reason. This base case should be working. If self of parent of x is equal to x, why isn't this working? Okay, we are reaching there. Okay, so 0, 1 is the problem. Parent of x is 0, x is equal to 1. So parent of x is equal to 0, and then we're returning 0. Self of parent, if x is greater, okay, we're connecting it, so Okay, so x is, so it printed it here. So x is lesser than y. Self parent of y is equal to x. Okay, this. Okay, it's 0 and 1. It's parent of, hmm, let me just return this for now. So that is something called path shortening, and I don't know if it's working, so give me a second. Okay, sorry for the disturbance. Okay, so there is a minor issue here. So what we're doing is we're calling self dot find on, let's say, uh, the child node. We have 7 here, and we're calling, let's say we want to find the parent of the root node of this, and we have to return. So if the parent of 7 is 2, we have to return the find function on 2, not the find function on 7 again. So that's the mistake. So let's get a path shortening again. So parent of x is equal to find of parent was self dot parent of x. We have to, yeah, we have to call the function on the parent, not the same node again. Okay, so self dot find, yeah, so that is the solution where it is not associated with the value. Okay, if the number of components is already okay, if the number of components is already k, we need a base case. So if if the uh, if k is equal to n, so then we return edges of, so the kth edge, right? We can remove all the other edges. So the fourth smallest edge. Is that right? We need the fourth smallest edge. Right, let's say we have 4 nodes, one, two, three, 4. So we only need 4 nodes to connect, right? So let's say one, two, 3 nodes to connect. But what if the third node is not connecting? So we can just remove it. Yeah. So one, two, these are the 3 smallest node connections. Okay, if k is equal to, hmm, okay, so if If k is already equal to n, we just return 0 because we don't have to connect anything. We have 4 and then k is also 4. So return 0. And this doesn't have to be here, so I can just add this here. I think it should be fine now. Okay, so we do have a mistake somewhere. K is equal to 1. Output is 42. Components is greater than. Okay, so let's run this. Does this work? Not equal to. Okay, okay, same issue. I don't think that was the problem. How do we address this? So let's just print out components, comma, x, comma, y, comma, w. Okay, so we have 6, 5. Okay, let us write on this once. So let's say we have 0, 1, 2, 3, 4, 5, 6. So we have 7 components, and now we connect 0 to 1, 6 components, 3, 5, 0, 4. So 3, 5, 5 components, 0, 4, 4 components, 3, 5, 0, 4, 1, 6, 3 components, 1, 6, 4, 5, 4 and 5, uh, yeah, 2 components, and then 1 and 5, they're already connected, so it doesn't matter. And then 1 and 3, 1 and 3, 42. Okay, 1 and 3 is 42. Okay, so the problem is root of x is equal to root of y. Return false. So, okay, now we still have 2 components after connecting 1 and 3. That's the problem. So after connecting 1 and 3, we still have 2 components. But for some reason, it's decrementing it by 1. Let us just print out so dsu dot find of x, comma dsu dot find of y, and let's see what's going on. Okay, the find is the same thing. It's both 0 and 0. So that is after connecting, right? So, or let me just add that inside union itself. So inside union, they're different, they're different. So we're gonna print, uh, let me create an F string, some stars, and then that is that it's an F string. So yeah, that seems fine. Let's debug this. Okay, here it's self because the object we're referring to is not instantiate. Hmm. Okay. So here 3 and 0. Okay, so X and Y. X and Y. X and Y is 1 and 3. But first of all, where's the node 1, 3 here? 1, 3. Yeah, 1, 3, 54. And the output they want is 67, first of all. Yeah, 0, 2. So 1, 3 is 54. First of all, why is it 42? Shouldn't we be 54 first of all? Okay, not Z, W. Okay, so 3, 6, 42. Okay, 3, 6, 42 is the problem. 3, 6, 42. And for that, we have the 3 and 6, right? So 3 and 6. The roots are supposed to be 0 for both of them. For one of them, root is 3 itself. Okay, so when we connected 3 and 5, um, Okay, when we connect 3 and 5, 3 and 5, because the head, okay, so that is, so, okay, I have too many statements here. Okay, so I did notice the issue with the thing. So what we're doing is, the problem was, let's say we have 2, and then we have 3, and then we have 4, and we have 1. And we want to connect 3 and 4. So what I was doing in the union function is, I was changing the parent of 4, sorry, the parent of 3 to 1. I forgot to change the parent of 2 as well. So what I was supposed to do is change the parent of 2 to 1, not 3. So here, uh, so self dot parent of, so to change the parent, to change the parent of the root of x and root of y, and now it should be fine. Yeah. So that was the mistake. So that was just DSC solution, DSU. Yeah. I still have to get better at Union Find, but I just thought the solution was really interesting, so I hope you guys liked it.